Understanding piecewise defined functions. Exploring piecewise defined function models. A piecewise function has different rules for different parts of its domain. The following situation can be modeled by a piecewise function. Armando drives from his home to the grocery store at a speed of 0.9 miles per hour for 4 minutes. Stops for 2 minutes to buy snacks, and then drives to the soccer field at a speed of 0.7 miles per minute for 3 minutes. The graph shows Armando's distance from home. The 3 different sections in the graph show that there are 3 different parts of the function. The function for this graph will have 3 function rules, each for a different range of values for x. The domain refers to the inputs. What values can you put into the function? Over here where it talks about rules, that's referring to different equations. It will have 3 different equation pieces, one for each part of the graph. It says the following steps can be used to build the piecewise function to model this situation. Determine the function rule for the first 4 minutes for the domain, from 0 to 4, that first gray chunk. The rate of change is Armando's speed in miles per minute. Up here it tells us 0.9 miles per minute. The y-intercept of that chunk is 0. So the function for the first 4 minutes, or that rule, is y equals m, which is 0.9, x plus b, the y-intercept is 0. Determine the function rule for the next 2 minutes for the domain from 4 to 6. That's the red section. It says because the distance is not changing, the rate is 0 miles in 1 minute, or a rate of 0. The function for the next 2 minutes is a constant function. The constant y value is Armando's distance from home at the end of the first 4 minutes. So if we take that first section and we plug in a 4, 0.9 times 4 is 3.6. Then it says determine the function rule for the last 3 minutes. The rate of change is Armando's speed in miles per minute. And it told us on the previous page he went 0.7 miles per minute. The point at which this function begins is 6, because that's the time. We had that first section, which was 4 minutes, and then another 2-minute section. So now we're starting at 6 minutes. And it didn't change the y value, so it is still at 3.6. Use the point and slope to construct the function rule for the last 3 minutes. This is point slope form, using y minus y1 equals m times x minus x1. These two values come from the point. So the point we have, the y value in that point is 3.6. And the x value in that point is 6. The slope was 0.7. Now we have to distribute 0.7 times x and 0.7 times 6. Then we're going to add 3.6 to both sides to turn it into slope-intercept form. Use all 3 parts to build the piecewise function that represents this situation. The equation for the first graph, or the first part of the graph, was 0.9x plus 0, but we don't need that part. Then the second one, it ended up at 3.6 the whole time, and the slope was 0, so all we need is that y value. And then the last one, we have 0.7x minus 0.6. And so you can see that the domain piece, the first 4 minutes, then the next 2 minutes, and the final 3 minutes. It breaks it up into those 3 different chunks from the graph. 1. Describe how the domain is constructed so that the piecewise function is a function with no more than one dependent variable for any independent variable. If we go back and look at the blue domains, the 4 only appears in this part, but it's not included in here because there's no equal to sign under the less than symbol. Same thing occurs with the 6. It is included in here, but it is not included here. So, the piecewise function is a function with no more than one dependent variable for any independent variable. And the reason for that is each value in the domain is only associated or assigned to with one rule or one function rule. It is not expected to behave in 2 different ways with the same input. It only has to work for one rule. Evaluating piecewise defined functions. The greatest integer function, which is also referred to as the floor function, is a piecewise function whose rule is denoted by this. These are not absolute value bars. They have these little lines on the bottom which tell us it is a floor function. There's also a thing called a ceiling function, which looks like this. These are not things that you should see too often in math, but they do pop up occasionally. So this represents the greatest integer less than or equal to the input, the value of x. The greatest integer function is an example of what's called a step function, which you'll see why in a little bit. A piecewise function in which each function rule is a constant function. To evaluate a piecewise function for a given value of x, we substitute the value of x into the rule for the part of the domain that includes that x value. Let me give you an example before we move on. If we had a number line, and I said, well, what's the value or the output for when x is 2.3? If I put 2.3 on the graph, the greatest integer function is going to give us the value less than or equal to x. So the closest integer that is below x, which in this case would be 2. If I were to take the floor function of negative 1.7, here would be negative 1.7, the integer that is just below that would be negative 2. If I had the floor function of negative 2.5, the integer just below that would be negative 3. Now it says, evaluate each piecewise function for the given values. If I put in negative 3 into the function, it says negative 3 is in that section, so it gives me an output of negative 3. If I put negative 2.9 in for x, and negative 2.9 is in the interval between negative 2 and negative 3, so it goes back to the closest integer below it, which is also -3. Then if we look at 0.7, 0.7 gets plugged in, and it is between 0 and 1, so the closest integer below would be 0. And then we have 1.06 plugged in, and it is between 1 and 2. The closest integer below 1.06 is 1. Now we have a different set of piecewise functions. It says if it is below 0, we use this function, and if it is 0 or above, we use this function. So since -3 is below 0, we have to plug it into the green function. Negative times -3 turns out to be a +3. Then we have -0.2, which is also below 0. So we plug that in, which gives us +0.2. 0 is 0 or above, so it gets plugged into the red function. So x plus 1, but now we have x is going to be replaced with 0, and 0 plus 1 is 1. And then we also have 2, which is also 0 or above, and 2 plus 1 is 3. So those are the outputs for those given inputs. 2. For the positive numbers, how is applying the greatest integer function different from the method to rounding to the nearest whole number? So if I had 2.5, that rounds to 3, but the floor function says to go to the closest integer below, and so that would tell us its output is 2. So we're going to say when rounding, if the decimal is 0.5 or more, we use the closest integer above. With the floor function, they round down. Even with 0.5 or above. Like 2.9 would still go down to 2. Find f of -2, f of -0.4, f of 3.7, and f of 5 for these piecewise functions. -2 is below 2, so we're going to plug it into that top function. If I take -2, that would give me +2. Now let's look at f of -0.4. That is also below 2. Negative times -0.4 gives me +0.4. F of 3.7. 3.7 is between 2 and 4. So we're going to plug it in here. 2 times 3.7 plus 3 would be 7.4 plus 3 for a total of 10.4. And f of 5 is greater than or equal to 4, so we have to square it. 5 squared is 25. You can graph piecewise defined functions to illustrate their behavior. It says for x less than 0, we use that negative x function. And so they've graphed that here. It has a slope of -1. And it has an open hole at 0 because it doesn't have the equal sign there. Then the second function, when x is greater than or equal to 0, it has an intercept of 1. And it's filled in because that equal to sign, and it has a slope of +1. Then it also says make a table of the values, which you can see they have written underneath. Now we're going to make a table of values for the floor function. If I put in -2.9, the next closest integer below it would be -3. If I put in -2.1, the next integer below it would still be -3. If I put in -1.5, the closest integer below it would be -2. If I put in -1, that is right on the integer, so it stays -1. For 1, same thing, it's on the integer, so it stays. 1.5, the integer right below it would be 1. And for 2, it's right on the integer, so it stays. Now we need to graph the function. So if I put in -3, I get out -3. And as I approach -2, I stay at -3 the whole time until I get to -2. So this side's going to be an open circle because once I get to -2, it jumps up. Then at -1.5, you can see it's still at -2. -1 is at -1, and as it approaches 0, it stays at -1, but as soon as it gets to 0, it jumps up, and so it takes on this look to it, which earlier I told you it was you would see why it's called a stair function. So you can see it occurring with that floor function looking like a stair function. It says, why does the example in 2a use rays and not lines? So a ray looks like this, and a line looks like this. It uses rays because it doesn't continue on forever in both directions. The intervals for the domain provide a starting place or an ending place. So it does not continue forever both ways. Use the graph of the greatest integer function from 2b to explain why this function is called a step function. Now it's our turn. We have the 3 rules with the domains on them. And so if it's less than 2, we're going to use x, which has a slope of 1. Keep in mind, at 2, we would actually use this function because it has the equals to 2 piece there. But we're going to figure out what would happen if we put 2 into this function as a guide to tell us where we need to stop. So if I put 2 into that function, 2 is the input, it goes in the x position, so we would get out a 2. And there's going to be an open circle there because it does not have the equal to symbol here. Then we are going to use values that are less than 2, like 0, for example. That would give me 0 as my output. If I put in -1, that gives me -1 as my output. If I put in -4, I would have -4 as my output. And so we're going to get a line pointed towards the left following that slope of 1. Now we're going to look at the next set of rules for 2 to 4. At 2, we have an equals to symbol, so we get to use f of 2, which would be 2 times 2 plus 3. That would be 4 plus 3, telling us f of 2 is 7, which means when you plug in 2, you get out 7. And that is a solid dot because it has the equal to symbol. Then we're going to continue on. If we plugged in 3, 2 times 3 is 6, plus 3 would give us 9. So f of 3 is 9. Go over to 3 and up to 9. And we also need to look at what happens at 4, but we're not going to say f of 4 because that would actually be plugged into that third rule. So we're just going to use like a scratch section on the side of our paper to figure out what it would go to for 2 times 4 plus 3. That would give us 8 plus 3, which is 11. So we're going to go 4, 11, but we're going to leave that one as an open circle. So that is that second chunk. Now for f of 4, we need to use this function, which is squared. So 4 squared is 16. So we're going to go over to 4 and up to 16 and put a solid dot. And then we're going to do numbers that are bigger than 4. For example, 5 could be plugged in there. 5 squared is 25, and that's off of our chart way up in here somewhere. And since it's an x squared and not just an x, it's actually going to be a curve. It's not a linear function, so this needs to have a bit of a curve to it. And that section in the middle does not have any arrows because it has a starting place and a stopping place. So it does not need an arrow on either direction, but the first one gets an arrow in one direction and the last one gets an arrow in the other because they just have a starting place or a stopping place, but not both. So that takes care of that. Some real-world situations can be described by piecewise functions. Write a piecewise function for each situation, then graph the function. This one is about travel. On her way to a concert, Maisie walks at a speed of 0.03 miles per minute from her car for 5 minutes, waits in line for a ticket for 3 minutes, and then walks to her seat for 3 minutes at a speed of 0.01 mile per minute. Express the Maisie's distance traveled, represented by D, in miles as a function of time, which is represented by T, in minutes. So for the first 5 minutes, her slope is 0.03, and her y-intercept, where she starts, is 0 distance or 0 miles from her starting place. And so the function is represented like so. That's just another way of saying y equals m would be her 0.03, and instead of x, we're using t for time. So it's just in a different method, but it's still the same format that you're kind of used to seeing. Then for the next 3 minutes, it says she waits in line. So from 5 to 8 minutes, she waits in line. So her slope doesn't increase or decrease. She's not walking farther or closer, so her slope is 0. And the y-intercept is 15. And the way that they got that 0.15, is by multiplying that 0.03 by the time that it took to get to that starting place or that place in line. Then for the last 3 minutes, so from time 8 to time 11, her slope was 0.01, which is where it shows up here. And we also have to plug in the point here from before. And they used point slope form like we did earlier to figure out what that initial value has to be. So they've written it in the form of a piecewise function. They've listed out the different intervals, and they've graphed the situation here. And you might be wondering why there aren't any open circles, and it's because wherever this piece started is the same place that it ended. So there's a full circle there where they overlap. Now we get to fill in some information. On his way to class from his dorm room, a college student walks at a speed of 0.05 miles per minute for 3 minutes. So that first 3 minutes, his slope is 0.05. And he's starting out, so his B value is 0. Then he stops and talks to a friend, so his slope is 0, for 1 minute. So his time went from 3 minutes to 4 minutes, because it was a matter of 1 minute. And so he stays where he is. If we plugged in 0.05 and we replaced the t with the 3 where he starts out his next section, that would give us that 15, which is where we got this piece from. Then for the next 2 minutes, it says, and then to avoid being late for class, he runs at a speed of 0.1 miles per minute for 2 minutes. So his slope is 0.1. Beginning at the point 4, because that's where he starts this section, 15. Point 15. So y equals, and we have to figure out what this is in point slope form. So we're going to use that same y minus y1 equals m x minus x1, which is 4. And then we will distribute. So we have y minus 0.15 equals 0.1x. And then 0.1 times negative 4 is going to be negative 0.4. Then we add the piece to the other side. We have y equals 0.1x. And if we had negative 0.4 and we add 0.15, we get negative 0.25. So y equals 0.1x minus 0.25. And now we're going to write those 3 rules into the piecewise function. Oh, yes, I was supposed to use t's instead of x's, but they switched them in there. They used a y and an x there, but then they used a t and a d for distance in this section. So you can see that they've started out with the 0.05 for the first 3 minutes. Then he stays at 0.15 until time 4. And then he takes off at a slope of 0.1. So he's going up 0.1 every minute. So in 1 minute, he goes from 0.15 to 0.25. 0.25 to 0.35. That went a little steep. Let's fix that. There we go. Finance. A savings account earns 1.4% simple interest annually for balances of 100 or less. 2.4% simple interest for balances greater than 100 and up to $500, and 3.4% simple interest for balances greater than 500. Write a function rule for the interest paid by the account and graph the function. So here we go. We have the first piece is for balances 100 or less. So if x is less than or equal to $100. They get 1.4% simple interest, which is 0.014 if we're writing it as a rate. And then in the next section, they get 2.4 if they had greater than 100 and up to 500. And 3.4 for balances greater than 500 or more. We could also write it like so. And this is going to say f of x on the side. And now we have to graph them. So this is in hundreds of dollars. So if they have $100, that would be 100 times 0.014, which would be a very small amount. Then from 100 to 500, at 100, they would take off and get 2.4, so there should be an open circle at 2.4. And then at 500 times 0.024 would be 12 for 500, so over to 5 and up to 12. And then for greater than 500, we would do an open circle. We would do 500 times 0.034, and that would be our open circle, which is 17. And then above, so you could see about $800 where that might be and see if you can graph that on there, or maybe $600. It looks like 6 is going to start to go off our graph, so just draw an arrow there. Building piecewise defined functions from graphs. You can find the function rules for a piecewise function when you are given the graph of the function. So it says, writing an equation for each graph. Find the equation of the ray on the right. They start out by finding the slope, which is up 3 and over 1. Because the point 1, 1 is on the ray, we're going to have a closed circle, or we have a closed circle, so we're going to use that equal to symbol in our inequality. And we can also use that to plug into point slope form. So we have y minus y1 equals m times x minus x1. We can distribute. That would turn into y minus 1 equals 3x minus 3. Then add the 1 to both sides, and we get y equals 3x minus 2. This function here. It says the equation of the line contains the horizontal ray is y equals -1, because all the y values here are at -1, and it has a slope of 0. So there is no mx piece, there's just the b value. Now, they set it up and they said, okay, well, this piece was for x values equal to 1 or bigger. If we're moving to the right on the number line, those x values are bigger. And you can see as it moves to the right, it is approaching that same 3x minus 2 line, or ray, excuse me. And then for the other piece, it is an open circle here. So it has the less than symbol, and it uses this function, or this rule. Moving on to B. Find the equation for the ray on the left. You can see here we have this point -1, 1, and here I have a point -4, -2. So we use the change in y, so that 1 minus another y value, and then over the change in x, so the x value minus another x value. When you have that 1 minus a negative, it changes to addition. So that is 3. -1 plus 4 is also 3 for a slope of positive 1. Then it says because the point -1, 1 is on the array, we can use y minus 1 equals the x, or the slope, times x minus x1. Then we would distribute 1 times that, and 1 times this piece, which gives us y minus 1 equals x, and then minus a negative changes to plus. Then we have to add the 1 to the other side, leaving us with y equals x plus 2. Then it says the equation for the horizontal array is y equals, and since the y value for every single one of those points is 3, that is our y value there. Okay. 8. First things first, we can start with either y or we can start with f of x. It looks like it doesn't matter in this case. And then we use our brackets for the two functions. This piece here is the y value is equal to 1. So we have y equals 1 when x is greater than 4, but not equal to 4 because it's an open circle there. This other piece, we have a slope of, looks like up 1 and over 2, so that would be a slope of 1/2, and an initial value of -4, and that is for when x is less than or equal to 4. You see here that it lines up with the x equals 4, and it's pointing to all the x values on the left, which would be less than 4. 9. How are the greatest integer function and f of x equals 2 times the floor function related? This just doubles the output. So for example, if I plugged in 1.7, this piece would turn into 1, and then it would give me an output of 1 times 2, which is 2. But if all I had was the original function, that would just give me 1. So the output piece is doubled. 10. How many function rules do functions that are not piecewise have? If it is not piecewise, they only have one rule. Functions that are piecewise have 2 or more.